Okay, good afternoon, everyone. Are you ready to learn some physics? So last class we learned about two types of charges, their properties. And in one of the property was that like charges repel. So that means if it's negative and negative, they repel, push each other away. And if they are unlike, different kind, one positive, another negative, then in that case, they attract. So now the question is, okay, if they are pushing each other away or attracting each other, then by how much? Obvious question, right? How strong is the force? So that's what we're going to be talking about today mostly. We will write the equation and we'll actually solve problems related to that. We'll calculate forces, okay? So for example, if we have two balloons and let's see, I copied this picture from somewhere. Three positive and more than positive. I mean, there is more negative than positive. So that's why the Q1 and Q2, they have net negative charge. So since both of them have net negative charge, they are repelling each other. So they are not sticking together, rather they are staying a bit separate from each other. So that's the repulsion effect. So how strong the force is going to depend on, of course, the charge, right? So there are charges, so it depends on charges. If there is no charge, there is no force. And once we have extra charges, then the force arises. So that means the force depends on charge. And similarly, if when they are very close, they experience stronger forces than when they are farther. So that tells us it's a distance dependence. So charge dependent, distance dependent. So turns out they are proportional to the product of charges. So Q1 and Q2, product of charges, and R, separation distance between them. Okay. So for example, in this case, here there is this Q1 balloon and let's see if I can use my pen here. Oops. Q1 balloon, Q2 balloon. So separation distance between them would be something like this, R. So that's what we are denoting. Okay. And there is K, which is basically proportionality constant, but also known as Coulomb's constant because this equation is also known as Coulomb's law. So actually you can find the value of K by designing experiment and then measuring the force. Measure the force between two charges. You know those charges has to be known, and you know how far those charges are. You can measure them. So once you have force and charges in R, you can calculate the value of K. And this one turns out to be this. We're going to be using just 9.0 times 10 to the power negative 9 Newton meter square over Coulomb square. And the unit of K basically comes from rearranging the Coulomb's law. So if I were to bring R this side, it's going to be R square over there. And there are product of Q's on the down there in the denominator. So that's why product of charges means Coulomb squared. And force in the numerator and distance squared in numerator means Newton square meter. And looking at this equation, probably you may recall force of gravity equation. So force of gravity is because of the mass of the objects. Okay, see how they are basically same equation. Only difference is masses versus charges. And another big difference is the constant here, gravitational constant. And gravitational constant, it is very small in terms of value. For example, it is, if I remember correctly, 10 to the power -7, but this is 10 to the power +9. So very strong. The electric force between two charges is very strong compared to the gravitational force between masses. So that's why we can easily experience electric forces even for small objects, but we don't experience the gravitational force between two masses, okay? Unless one of the mass or both masses are huge, planet size, right? So basically it's the same thing. So we learn about gravitational force, which we said was, okay, long range force in physics 1. That's what we learned. Long range force means it can act without contact. Okay, it can act, object can interact without touching, just like mass over here cannot interact with the earth without touching. If I let it go, earth hasn't come and touch and pull it down, but it goes down, right? So that means it's happening without contact. So action at a distance. Same thing is true for this. So this is another kind of long-range force, okay? It arises because of the presence of charges. Gravitational force that arises because of the presence of mass, okay? Only that's the difference. And since we're taking account of charges, so we have to have charges in the equation, okay? So square distance square relationship or inverse square relationship with the distance, it's the same thing, okay? So now this is what we call electric force, not gravitational force, but their nature is exactly same. So this is a little bit more complicated than gravitational force. It's because mass, they always attract, they don't repel. But in case of charges, they may attract and repel. So for example, so this we use to calculate the value of the force. Now we need to know how to figure out direction of force, right? So direction of force, we just use that property. Like charges repel. So if we are looking at the forces between these, so positive charge, so this is force on this charge because of this charge, okay? Similarly, this charge experience force because of this charge and it's pushing away. So they act along the same line, okay? So you cannot draw one, for example, going straight, something like that, another one going something like that. That would be incorrect, okay? So when they are same, so they repel. So that's why the balloon here has a negative charge, extra negative charge. So it's going that way, and that one is going that way. So why it stopped? Why did not it keep on going? So for that, we have to take account of its weight. See the balloon, they have mass, that means they have weight. So this is electric force, but this is gravitational force, and there is this tension force. So the balance among these three forces keeps them in equilibrium at that point, okay? If you push them closer, they're gonna move away, and at certain point, what happens? They comes in equilibrium. So that's when these three forces, tension, the electric force, and the weight, they are balanced, okay? So now, so this is similar charges and repelling each other. Now, if we look at the opposite charges, we should be able to draw the force. So this positive charge is being pulled by negative charge like that. And negative charge is at the same time getting pulled by positive charge. And these forces, by the way, whether they are attractive or repulsive, they have equal value, like Newton's third law of motion, action and reaction. They are like action and reaction. One is acting on another one, and another one is reacting, right? So same thing goes here, right? So that's how we can draw these forces again along the same line that connects the charges. Okay, so one charge here, another charge here. The line connecting those charges are that means the force is going to be either that way or that way. Repulsion, attraction, and both repulsion and attraction does not act at the same time. Sometimes they attract. When do they attract? When charges are unlike, positive and negative, they attract. But if we have negative, negative, they repel, and so does the positive and positive. Okay, so that's the force calculating, like formula for calculating value of the force and figuring out the direction. So it is a vector quantity, of course, force. So we need to take account of that. Okay. So now here is a question. So there are numbers, but you don't need to plug in this. If you can, look carefully how the things are changing. For example, separation distance goes from 10 centimeter to 20 centimeters, right? So separation distance is doubling. What's going to happen to the force, right? So what do you think? So I'm opening the poll. Go ahead, poll on it. And you have a minute and 30 seconds. Maybe we'll do 2 minutes for this. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see how did we do here. So we are all over the places. There is a little bit more for the B, right? But we are everywhere. So it looks like we need to pay attention. So in this clicker, I don't know who made mistake and who answered correctly. All I can see is just what I showed you. Okay. So What went wrong? A lot of you made mistake, no matter what, whether the correct choice is. Okay. So this is the equation that gives us force between two charges. And here the force is known. Force is given for one separation, right? So R is given, K is constant, and charges, those values, they are not changing. So that means they are constant. Charge values are not changing. K is always constant, of course. What is changing? Distance changed. So when distance changes, force changes. And first of all, you want to look if the force increases or decreases, right? So this distance is in denominator. So that means when R increases, what happens to the F? See, they have inverse relation. F is in the numerator on the other side. This is in denominator. So they have inverse, what we call inverse relationship. So when R increases, F decreases. Just knowing that, you can eliminate. For example, this was 0.5, so it cannot be 0.5, right? Cannot be 1 Newton. It has to decrease. So it has to be either this or that. So now, how is it related to distance? It's not just R. If it was just R, then by doubling R, if it were just R, then by just doubling R, you are making it half because it is in denominator, right? Doubling R, you are making force half. But this is not just R, it is R squared. It's not just inverse relationship, it is inverse square relationship, okay? So that means when we square this, so it has that. So that means when R doubles, it has to be squared. So when we when we square the double, what happens? This becomes 4R squared. So this 4 is in denominator. So that means force is now 1/4 of whatever it was before. You double the distance, force became 1/4. So what is quarter of half? So that means you need to divide this 0.25, no, not 25, but 0.5, that is the original force, by 4. So looks like quarter of 4 is this 12.5. So looks like A is correct answer. See,
Ramesh, the part of the question says that the charge of one of the spheres is doubled. Does that still mean that Q1 and Q2 remain constant, or does that mean that,
oh,
yeah,
it wasn't just the distance. That's
yeah,
yeah, I did not read that. Glad you reminded me. Okay. So yes, so charge increased. So it became quarter because of the doubling distance, right? And charge is also double. So charge is not constant. Oops. So that means charge, one of the charge doubled means, so let's say if we double Q1 to 2Q1, now the new product gonna be 2Q1 times Q2. So there is this 2 times over there as well. So yes, looks like it is just became half, not quarter. Yeah, I did not pay attention to that. Okay. So that means looks like we have B as the correct answer. So without plugging in number, we were able to calculate it, but you can also plug in numbers and get the answer if you like. Okay. You have to write equation twice and divide one equation by another equation, and things are going to cancel. So for example, let's say at one point, what happens? We have this k q1 q2 over r square, and now new force is k, and let's say 2 times q1 times q2. I'm saying 1 is doubled, and then r on the other hand became 2 times r, so you need to square that. So this way it's better than plugging in centimeter, 10 centimeter here. Okay. So now what happens is that this becomes k q1 q2. So there is 4 and there is 2, and because of that I can do this. So if you compare these, so f new divided by f is, you need to divide this by this. So that means it's going to be k q q1 over 2r squared times. Now divide, so fraction of fraction, so we can flip it, and it becomes, oh, I should be writing q1 here. So now you see this cancels, and r squared cancels. So we have half in this side, so f new is half of f. Half of 0.5 is quarter Newton. So this is systematic way of doing it, but you don't have to do all these. You can just look at the equation and see how things are changing, and you can do it that way too, whatever you feel comfortable. Okay. Again, thank you for reminding me that the charge was also changing. Okay. So anything you like to ask or add here? Okay, if not, then I'm going to ask you a question. So this question is about direction. So that was about magnitude, and this is about direction. And you have a minute to answer this question. See, there is a positive charge here. Oops. And there is positive charge over there. Hopefully you can see it. And A, B, C, D choices are right there. This is C, by the way. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, so let's see how did we do here. So we have again B. Okay, but we also have C and quite a few D as well. So D would be the case if one of these was negative, either this negative or that negative, then D would be answer. But in this case, like charges, they repel means pushing away, right? It says, go away from me, stay away from me, okay? So that's why how they behave, like charges. And so this one is pushing this one away means B is the correct answer. Okay, I already chose that. Anything you like to add on this? Okay, now let's look at a bit more challenging than these. See, on the left hand side is the same charge, but on the right hand side there is Q and double of Q, 4 times of Q. But at the same time, distance also double here. Okay, distance double here. Charge doubled, distance doubled. Oh, does that sound familiar? Okay, so I'm going to open the poll and you have 2 minutes. If you need, write them down. Okay, so for example, force between these two are K, Q uppercase, lowercase q over R square, and force between these are K, Q, 2Q, and 2R squared, and so on. Okay, and compare. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see how did we do here. So we have C and E competing, huh? And others are also following behind. I don't know the answer, I have to do it. So just like we had that question 10 centimeter versus 20 centimeter and doubling one of the charge, looks like between these it's exactly same. Okay, so if I were to write it, it's going to be K, Q, and uppercase Q, and there is this extra factor 2 R squared. One of the two going to cancel because we have this being squared. And then now, let's say if I were to write F2 over here, this, I guess based on the question, maybe it's a good idea to write F on 2Q, F on 4Q, right? That's how the question is formulated. So let's write something like that. So in this case, what happens is the charge doubles. One of the charge doubles, sorry, becomes 4 times more. Not just doubles, but 4 times. And over here, it becomes 4r squared because 2r squared is 4r squared. So this one cancels, giving us just k q q over r squared. So now this one here is same as this one over there. And this one, force on this one is only half of those. So looks like Q and 4Q, they are same. So that means E is the correct answer in this case. Okay? So there were quite a few C as well. So what happened here? Q and 2Q are same. So again, probably you forgot to double the distance, r squared, right? So 2r squared means 4r squared. Never forget that, okay? Never forget that. So over here, what happened is, because of the charges, numerator became 4 times larger, and because of the double distance, denominator also become 4 times larger. So that 4 times effect got canceled, okay? So now the question is, does Q feel the same amount of force that experienced by lowercase q? So in another word, do they experience same amount of force? So I guess it's better if I make clicker question. Let's say A is yes and B is no. Okay. So right now I'm going to be pulling on this one and you have 30 seconds to respond. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. So let's see what we got here. So mostly A, that is correct answer. Action, reaction. See, this is the force between two charges. Okay, the value we are calculating is force between two charges, and it's like action, reaction forces. Okay, whatever amount one is pulling with, another one is pulling with the same amount of force, and vice versa. Same thing goes with that. If that force is F, that force is also exactly F. Okay, so it looks like there is some comment or question on the Zoom chat here. In 2Q, F2Q, does not 2 from 2r squared denominator cancel out because of the 2Q in the numerator? Yeah, it does. So that's why it is only 2r squared. Otherwise, it would have been 4. Okay, so what happened was this 2Q and this is 4r squared. So this 2 canceled with this 4, giving us just 2 over here. And that's what I wrote. Okay. So yes, it did cancel. Okay, so now let's go back to physics 1, vector thingy, adding two vectors. One is acting to the left, another one is acting to the right on the same object. What is the force acting on the cube? Force or net force? Same thing. Okay, so that's the question. And you have 2 minutes. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got. So mostly C, but is B as well. Both of them are 2 Newton. What's the difference? Why 2 Newton or negative 2 Newton? Can somebody explain? Can you turn on your microphone and help us?
I said C because according to the little vector at the top where it says the y direction's positive at up and then the x direction's positive at the right, since our little block was getting pulled 12 newtons to the left, that means it's going in the negative direction. So then you do negative 12 plus positive 10 since it's going positive 10 in the right direction and you get negative 2.
Perfect. I couldn't have done it better. Okay. So here it means one is positive, another one is negative. So even if this wasn't given, you need to, you can do that like positive this and negative. In that case, that would be 2 Newton. But based on what coordinate system given, it has to be negative 2 Newton. Okay. So this means on this direction, whatever force going in that direction, that is positive. So that's how I write it. And the one that goes to the opposite to that is negative. So that's why I'm writing like that. So now the net force is sum of F1 and F2. But one is positive, another one is negative. Positive times negative is negative. That's why it is negative 2 newtons. So we're going to be using this idea for the problem I have brought here from our note. Okay. So it is done in detail in note. I have another problem, similar problem. We'll do that. But let's see how it's done here. So there are 2 charges. and third charge is in the middle. So the question is asking us calculate the net force exerted on Q2 because of Q1 and Q3. So that means we need to first sketch how the forces are acting. See, now the things we learn from clicker question comes out handy. So this is positive, this is positive. So that is repulsive force. So that means this is telling this charge, go away from me. Go, 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 go away, right? So that's what it is saying. So that's why I am showing that force F1 as the force from Q1. Okay, so force from Q1 charge, I am denoting that as a F1. And then on the other hand, there is Q3. It has a negative charge and it is positive. So that means it's attractive force. So that means what this charge is telling to this one, hey, come to me, come to me, come to me. Okay. So it is also acting in that direction. So that means both of these charges are acting in the same direction. So if we are to assume that as a positive, then these two gonna add. So F net gonna be F1 plus F2. So that's the direction, and because of that direction, we can tell whether we need to be subtracting them or adding them. Here, we need to be adding because both of them are pointing in the same direction. Now, before we get that final answer, of course, we need to find the value of this one and value of that one. So far, we talked about direction. And that helps us to tell, okay, it's going to be pointing that way. So just looking at the direction, we were able to figure out direction. So for the direction, this is how we do it. Now for the value, we just plug in the formula and punch in the calculator. Okay. So that means F1 is the force between these two charges, right? So that means in that formula for calculating F1, it's going to be K Q1 Q2 over R1 squared. But we have to be careful. This is 5 centimeter. So that has to be converted into meter. And there are 100 centimeters in a meter. So that means it's going to be 0.05 meters. Okay. So we need to plug in those. Another thing, oh, that is microcoulomb. So that means it is 4 times 10 to the power negative 6 coulomb, Q1. So Q1 is larger than Q3 in terms of value. So that's why I have drawn that F1 arrow larger. See, without doing calculation, I can tell, hey, same distance, but this charge is larger than that. So that means the force this is exerting must be larger. I can tell that. Okay. So similarly, to calculate F3, oh, it was F3. Why did I write F2? So F1 and F3. That's how I have denoted. Okay. So to calculate F3, you do the same thing. Okay. Now, this is the force between these two charges, means it has to be Q2, Q3, and R3 squared. Okay. So here, there is this negative sign. So negative sign only tells us about direction. It does not say anything about value. So to calculate the force, we will simply use the value of the charges. So you don't plug in negative number here, okay? Direction, you want to take care by drawing the arrow and just plug in numbers. So this is from the note. It is done in the note, and I cropped that page and brought it here. So that's how this number looks like. Okay. And Of course, you can use this as a 9.0 and the answer not going to be much different. And that's that. And when we add them, we get this. And I'm rounding this to 50 Newton because it is one sig fig problem. Okay, just one significant figure. So that's why I'm rounding it to just 50 Newton. Hopefully these numbers are done correctly. You wanna check? So first time I'm preparing these notes. So I'm, currently writing these notes. So there are going to be typos and so on. And similarly, I'm also this first time making the questions on the canvas for you folks. So sometimes you may see miskeyed and so on. So if you find something wrong or anything like that, please kindly let me know, write me email, okay? So now here is basically similar question. So can you, so in this case, this charge, see, this is negative charge now at the middle. This charge is given, this charge, both of these are positives, okay? But Q that is in the middle is negative, distances are given, okay? So can you draw, so let's say here is that charge Q. Can you draw the force due to Q1 on Q? Let's say that is F1. Is that in that direction or that direction? Draw it here on this dot. Okay. Which one is that? Or maybe I can make clicker question. So you think about it, I'll make clicker question. Force on Q due to Q1 is pointing to the left or right. Okay. A is, let's say, left, and B is to the right. And this is Q. Keep that in mind. So now I'm opening the poll, and you have 30 seconds to respond to this. So these are the steps you have to go through, okay, while solving this kind of problem. So it is not just the force between two charges, but three charges. So you need to calculate two separately. Okay, let's do 30 more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. So it was because of the Q1 I'm talking about, right? So Q1 is positive and Q is negative. So there is attractive force, means it's going to be pointing in that direction to the left. So that means A should be the correct answer. Oh, it's still a lot of confusion, huh? So this negative, this positive means attractive force, means attractive means pulling force. Think something like that. Okay. So A, I'm glad I made this clicker question here. Oh, I could keep that right there, Q. And let's say this is B, this is A. Now I'm saying Q2. Q on Q due to Q2 means this one here, okay? So we learned that F1 is pointing this way. Now, how about F2? That's what we need to figure out. So that's why this question. And now this time really 30 seconds, okay? Five more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see how did we do here. So mostly B, but there is quite a few A as well. So B is correct answer because negative and positive attract. We are talking about force on this means it's going to be pointing this way. So that means F2 going to be pointing that way. So now if we choose, let's see, what's going to be F net then? So to add them, remember, we cannot add left and right until we assign the sign for the direction. So let's say this is positive. So that means F2 is positive and F1 is negative. So we know the sign. Which one you think the value going to be larger? It's hard to tell, isn't it? So distance doubled here and charge became 4 times double. Charge doubled, distance doubled. Did we know anything about that thing in there? So the force here, this force due to this one, 4 Coulomb charge, is half of whatever we have from this one. Why? Because this is 2 times farther. 2 times farther means half, sorry, the quarter force if the charge wasn't doubled. But since charge is also doubled, so that means from the doubling charge, force doubled. But by doubling distance, force became quarter. So 2 on the numerator, 4 in the denominator means only half. So that means F2 is about is exactly half of that one. Okay, I can tell. But you don't have to take my word. You can do the calculation. Okay, so we figure out. So in this case, the net force is going to be pointing this way, and we'll find that by subtracting F2 from F1. So F net going to be F1 minus F2 because they are in opposite direction. One positive, another one negative. Okay. So if you take this as a positive, maybe we should write this if we take this as a positive. But if you choose this as a positive, you can do F1 minus F2. But anyway, you're going to be finding net by taking the difference because they are pointing in opposite direction. So that's how systematically you have to go about solving this problem. And conceptually, this problem is done. Only thing remaining is just doing the dirty work. Hopefully, the mostly calculator helps us, right? So F1 is K Q1 Q2 over R1, let's say, squared. So that means it is 9.010 to the power positive 9. So I'm going to be writing 9.0, okay, rather than writing 8.99. And then Q1, 2 microcoulomb means 2 times 10 to the power negative 6 coulomb. And Q is negative 1, but we just write 1. So that means it's going to be times 1 times 10 to the power 6 is just 10 to the power negative 6 coulomb, right? So that is in the numerator. How about denominator? So R1 is 0.01 meter, right? And since all these numbers are in exponents, maybe it's a good idea to write this as exponent as well. So 1 times 10 to the power negative 2 meters. Same thing, okay? So that way, if I were to square that, what's going to happen? 10 to the power negative 2 becomes 10 to the power negative 4, okay? So now you can combine these. So it looks like this negative 6 is going to be negative 12. But there is positive 9, so that means this is going to be negative 3. And this negative 4, when it goes to the top, it becomes 10 to the power positive 4. So basically, all the exponent gives you 10, a factor of 10. And how about the remaining? 9.2, sorry, 9 times 2 is 18 times 10 is 180 Newton. Oh, turns out to be a very large number. So I may be wrong because I'm doing that in my head. You want to verify using the calculator. And if I'm right, when I was talking about before, F2 must be 90 Newton, half of that. You do the math by plugging in numbers just like that. So that means F net gonna be so this one 180 Newton left, and this is 90 Newton, right? Right? So F net is, let's say, if right is positive, just like we said over here, then it's going to be positive 90 Newton minus 180 Newton. That means negative 90 Newton means 90 Newton to left. Okay, anything you like to add? Did you do your numbers? Okay, so that's how we do it, okay? So in this case, what do you see? There are 3 charges along a straight line, but there can be 3 charges, something like in triangular pattern, right? Q1, Q2, Q3, something like that. Then how do you do that? Process is exactly same. You calculate 2 forces and you add them vectorially. But in this case, acting vectorially is going to be a bit challenging because you may have to find components. Do you remember finding components of vector in physics 1? Okay, so we're going to be using that idea. But before we do that, let's take a break. Okay. So I'll see you in 5 minutes. So when we have two vectors, neither pointing in the same direction or opposite direction, in that case, we have to add those vectors using these different techniques. One of the technique, for example, adding vector. Remember we learned in physics 1, adding and subtracting vectors, right? So to subtract vector, you can put tails together and go from tail of initial to final, or the one that is subtracting to, the negative vector. So that's what we learned. So for example, if we are subtracting, we did something like this. So if we are finding VF minus VI, then what we do? We do that, and that would be delta V. So this is subtraction. Here it says represents the sum, means addition, right? So we learned, so we call this tail to tail, and then tip to tip. But for adding, what do we do? Tail to tip or head. So now, with that reminder, I like you to try this one here. You have 1 minute and 30 seconds. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see how did we do here. So mostly A. Is that correct answer? So we bring tail to the tips, tail to the tip, and draw like that. And it's gonna like that. So yeah, it makes sense. So what happens when we are adding two vectors, and if we are drawing something like this, tail to tail, it goes somewhere between, okay? It goes somewhere in between when we are adding. So now why that's the case, why I'm reminding that? So if we look at this problem, again, this is from my note. If you look at this problem, there are these three charges at this vortices of a right triangle. And we are asked to find total force on charge Q3 due to Q1 and Q2, right? So by looking at this is positive, so that means it's going to repel. So it's going to say go away, it's going to push. and it pushes along the line that connects them. So that's why F1 gonna be acting that way, not this way, not that way, not that way, no, 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 rather that way. Q2, on the other hand, is negative and Q3 is positive. So that means there is attractive force between them. They are pulling each other. So that means this is getting pulled that way. So that's the force I'm calling F2, and that one I'm calling F1. Now, see these two forces, like remember how we had in the previous question, PQ, something like that. Now we have similar two forces kind of pointing, kind of something like that, right? F1 slightly different. So we need to add them. But to find the value, if this triangle is not right triangle, then we cannot use just Pythagorean theorem. By just using this method, for example, let's say if I were to do that, okay, so that's going to be that. But we cannot use Pythagorean theorem here because this angle between these are not 90 degree. So in that case, what you have to do is you need to find the component of one of those. For example, you can find component of this, and then, for example, this is going to be x component here. Let's say if I say this one as a x, so f1x and f1y, it's going to be pointing down. Let's say if we say up positive, that's going to be negative. F2 is pointing right along this direction, so it has only one component, which is F2, which is the x component. So we don't need to find component of that. So to find component, we need to find angle. So in this case, since we know this side, we should be able to calculate this angle. Once we have that angle, then you should be able to write this component as a F1 cosine theta, this one as a F1 sine theta, and so on. Once we have that, then you find the total in this direction, total in that direction, and that's going to make right triangle, okay? So it's a long process and one of the very difficult problem we do in this class. And I have done this in detail in the note because of that reason, okay? So you can go step by step and hopefully understand. So x component here, y component here for F1, okay? And here this angle theta, which is same as this angle. And we can calculate that angle using this original triangle here because we know this side, we know this side, okay? That means we also know this side, 4 plus 3 is 5 actually. So, which is done here. So once you have added the components, then you can put them in tail and tip. That makes right triangle. That way you can find value and direction. Okay. So that was that, and that is done in the note in detail. Now let's do it one over here ourselves. Okay. Here. So do you remember the process? You need to find one force, you need to find another force, and you need to find a net force. The process is same. Depending on how they are oriented, it may be a bit challenging. So the values of the forces, I mean charges and distances, I kept them same. But only difference in this case, so same as not the note, but the problem we did before, right? So I'm keeping value of charges and the distance same so that we can use the same number for the force, okay? But the total gonna be not the same because they are not along the straight line. So what we need to do? So this is asking us what's the force on Q due to Q1 and Q2. So that means we are looking force here due to this one and that one. So if we were to break this problem, we need to find force on Q due to Q1, right? So Q1 is here and Q is over here. So the force gonna be in what direction? Is it gonna be that direction or that direction? So I'm saying, okay, that is, let's say force on Q1 is F1, okay? So F1 either is gonna be repulsive or attractive, right? So that means is this the F1 or is this one, okay? So A or B. So I'm gonna open the poll, okay? Did you understand the question? So this Q is this Q here, and I'm just talking about this force due to this Q1 on Q, okay? What is the direction? Not the value yet, just the direction. What is the direction? So that's what I'm asking, okay? And choices are here, just two choices. So you have now 30 seconds. Go ahead and poll, A or B. Five more seconds. 5, 4, 3, 2, 1, and it stops. Okay, so these two charges, they have opposite sign. That means unlike charges, opposite charges, they attract. So that means this positive charge is pulling this in this direction. So that means A should be the correct answer in this case. Okay, but I'm still getting quite a few B as well. Opposite charge attract means they pull towards each other. So when we are looking at force on this one, it must be pointing that way because of that. Now, I'm gonna say, okay, this is force F2, force on Q due to Q2. I'm calling that F2. So what is the direction of that on direction of force F2? Okay. So this is force on Q due to Q2. So is this away or towards Q2? Okay. So let's say this is A, this is B. So what is the answer? So I'm opening the poll and you have again 30 seconds. Remember, force always acts along the line connecting them. So that's why we have only two possible choices here. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay. So now this is negative, Q is negative, and Q2 is positive. So that means attractive force. Attractive. So Q2 is attracting. This being positive, here it's being negative, it's getting pulled. So that means it's a B. This one got a lot better. Okay, we are improving, right? Okay, so now what do we know? We know the direction of these two forces, so let's draw them, both of them, okay? The one is pointing this way, another one is pointing that way. We said that was F1, said that is F2. So now we need to calculate those values and add vectorially. So this is a bit easier than the one that I have done in the note. Why? Because these are making 90 degrees. So that means we don't have to find component in this case. They themselves are the components. Right? So which one is bigger? Which one is smaller? Double charge, double distance. So that means force between them is half. So F2 is shorter. And actually we did calculate these numbers in the last, the previous problem I did. Remember we had charge like this, same charges, but they were lined up like this. Now they are in triangle. So we calculated them. So it's the same thing, process is exactly same. So I'm going to be just writing value. F1 we had was 180 Newton, if I remember correctly. And F2 is 90 Newton. Now we need to add them. So we cannot just add these numbers because they are not pointing in same direction. We cannot just subtract them because they are not pointing in opposite direction. Rather, they are making 90 degree. So same direction, opposite direction, they are easiest to calculate. Once you have calculated F1, F2 and figure out which way they are pointing, they are easiest. And then next easiest is this one. And one that I showed you that is on the note over here, that is not the hardest one, but it is harder than the other one because they are not making 90 degree here, okay? But both of them could be going something like this, see? So in that case, you may have to find component of both of them. So I'm talking about components. If you took physics 1 with me, even if you don't remember or still know how to do it, probably you still remember we talked about components. But if you took physics with somebody else, most likely you heard about components, you used components, okay? But if you did not, then I have a video on YouTube that I actually asked before first class to my physics 1 students, okay? So the name of the video is trig, basic trig or something like that. Basic trigonometry for physics student or something like that. So in that video, I show you the details on how to do it. So if you have to refresh your memory, go and do that. And what is my YouTube channel? By the way, last class I recorded and posted that on YouTube, and I have posted link in Canvas, if I remember correctly. Okay. So if you open that link, you get to my channel. If not, the other way around, you know my name, at least you have my name, even if you don't know it. Okay. So Ramesh Dungana, there are quite a few of them in YouTube channels, turns out. So I have added this my degree as well. So search Ramesh Dungana PhD and you'll find me, and my photo has sunglasses on. Okay. So that's how you find the components. So that's you want to learn there. Oh, 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 what is this? Okay, so we not quite done on this one here. So now we have F1 and we have F2 and we want to add them. How do we do that? So we can use now tail to tip rule here, right here, because they are already 90 degree. If they are not already 90 degree, then you need to find components. And the sum of the components makes the 90 degree. That's the reason behind, finding components. But these are already 90 degrees. See, one is pointing this way, another is pointing that way, means the angle between them is 90 degree. So that means we have F2 here, we have F1 here, and to add these, we can just draw from tail of the first vector we drew to the tip of the last vector we drew. So that is our F1 plus F2 vector. So that means this we get, so F net, we get by using Pythagorean theorem. This is right triangle, so it's finding hypotenuse of, this. And if you don't remember this, this is also in the same video as well. So the F net, the value gonna be F1 square plus F2 square, side length squared under the square root, right? So you can use that and find the net value here. So I'll let you work on this one here. And then now this is value, but force being a vector, it also has a direction. So we need to find direction. So to find direction, we can find the angle, one of the angle here. Let's find this angle here. And let's say that angle is phi or theta. We haven't used theta here, so it's fine to use theta, but I'm using phi here. So this being right triangle and this and that we already know, we just calculated hypotenuse. So we can use any trig function we like, but it's a good idea to use with the original ones. So tangent of phi is opposite. See, this is opposite, means F1 divided by adjacent F2. So phi gonna be inverse of F1, F2. So that means F1 is 180 and F2 is 90. 180 is exactly double of 90, so that means it's inverse tangent of 2, and this is where calculator comes in handy. Okay. So I'll let you use your calculator. So some calculator have inverse tangent function like that. Other calculator may say arc 10, right? We also have calculator in our computer, right? Let's see if I can find that easily. So if you are using this, you want to choose scientific. And then now, here, let's see trig function. How does it names? Oh, there is no inverse function here, so I need to click on second. So now I see the inverse function, so this is what I'm looking for, right? But before I click on that, I need that 2 first, I think. I think that's how it works. And then inverse tangent. So that tells me the angle is 63.64 degrees. But this being just one sig fig problem, you want to round it to 60 degree. Okay. Which angle is 60 degree? Ooh, that was the angle made with the F2. right? So F2 is pointing that way, F1 is pointing that way. Our F net is that. So this is the angle we found. So that makes that many degree line joining the Q and Q2. If you want to find angle, this angle, you can now do it. So that is going to be 90 minus this pi or 60 degree. So it's going to be around 40 degree. Okay. So physics is simple in this case. Just plug in formula and calculate forces. And remaining thing is mathematics. It's a vector mathematics. Okay. So that makes this problem a little longer. Okay. Otherwise, it's not that bad. So don't get afraid. So anything you'd like to add or ask here? Okay, did anyone calculate magnitude of F net? I did not.
I got 201, I think.
So we need at least from 3 or 4 people. Can you type your number if you calculated? Can you type that on the canvas? The one that matches most likely going to be right. So let me clear all that. So 180 square is that, and then plus 90 square, that is 8100. I can do that on my head. And now let's take the square root. So 201 something. So when we do the approximation for 1 sig fig, rounding to 1 sig fig, it's going to be 200. Okay. And Newton, of course. And did anyone check if this 180 and 90, they are right? I did not check that, right? Okay. I see at least one thumbs up from video. Okay. Okay, that is force. So we learned about gravitational force, and now we know about another similar force. We call that electric force. And do you folks remember gravitational field? Field, football field, soccer field, field near that net, okay, that goes around, field. So when ball is rolling on the field, or let's say football is thrown on the field, what happens? Everyone looks at that football. Where is it going? It attracts, right? See, what is it attracting? Let's say it's creating field. So it pulls you, it influences you, it makes you look, scream, cry sometimes, right? So the idea is same, field idea of the field is same. So there is this earth sitting there, in the space, and it creates field. And any mass we bring near this, what happens? It experiences force. So field is there. But when we bring this mass experience force. We are also that kind of mass, so we experience that force. Force is everywhere around the earth. So we call that force field. That is a gravitational force field. Now, when we have a charge, what happens? Okay, if we bring another charge, so there is this charge, let's say one charge, we can call that source charge. Any charge can be called source charge, okay? We can call this source charge and we say, okay, it has field around it. Field, okay? And then if we bring another charge, just like near the earth, when we bring a mass, that mass experience force, right? Similarly, this one experience force as well. This force is electric force, not the gravitational force we're talking about. Yes, they're going to be gravitational force as well because they have masses. But their masses are so small, gravitational force is negligible compared to electric force. So we don't even have to worry about gravitational force between these charges. It is like a billion times more. What is billion times more? I don't remember exact numbers, but let's say it's many multiples more. What is many multiple more? Electric force is many multiple more. So for example, if you have one electron, one proton, they have same charge, but their mass is different and mass is tiny. So let's say m electron, m proton. If you calculate gravitational force between them, let's say separated by a distance 1 meter, and do the same thing here, what happens is the force you get between these two charges is way, way more than the gravitational force between mass of proton and mass of electron. So that's why we ignore the calculation of gravitational force between them when we talk about force between charges, because the electric force is so strong. If we are adding, for example, let's say if one has 1,000,000, another one has just one, for example. It's like saying, okay, I already have $1,000,000. Do I care about $1 much? But if I have just $1, then of course, that may give me a snack. I may buy a couple of apple out of that. Lot of value there. But when I have 1,000,000 already, and then one, I may say, okay, I'm not gonna say I have 1,000,000 and $1. I'm gonna just say $1,000,000. Okay, I have $1,000,000. Kind of same idea. Electric force between them is so strong, we don't even care about the gravitational force in most cases, okay? Unless you are specially asked to do it. In some cases, we'll look at example. For example, there is one example in my note that may be in another note that I'm going to be posting for the another class, or my long version of note. By the way, I'm in the process of making note and deciding how much I should be teaching in a particular class. So I had first posted a longer note, and then I posted shorter note for this class, okay? And part of that longer note gonna appear in for the next class. I realized I cannot cover all those looking at these long problems, okay? Okay, so that's the field idea. So electric field, so there is charge and there is charge around. So how much force per unit charge, we call that field. force per unit charge. And we define or write equation something like this. So if you already know the total force and force on this charge, and this charge sometimes also called test charge, this field is coming from whatever it is coming from, we call that source charge. Okay. So if we have, let's say, a 2 Coulomb charge and it experience 10 Newton, then 1 Coulomb charge is going to experience how much? 5 Newton. So 5 Newton per Coulomb is electric field. So this is just a force in disguise. Okay, force in disguise. So force between two charges, but field at a point. So we don't need two charges for the field to be there. Just like we already have gravitational field around the earth. We don't need another object, another mass. Okay. Once we have a charge, it creates field. Once we have a charge, it creates field. But to check if there is field or not, what you need to do, you need to bring a charge. That's why we call another charge, we call that test charge, and that experience force. So for example, magnet, you are familiar with, right? I may have a magnet here, tiny bit. See, when I'm holding this magnet alone, just one magnet here, I don't know this is creating field or not. To check that, if I bring another magnet, for example, nearby, and then now I feel, oh, there is pull. That means there is magnetic field. So we can say, okay, this is source for the magnetic field, and this is test magnet. Similarly, we can name, so not in a particular order or anything like that. Just one is source, another one is test. Okay. So we divide the field force between source and test. That is the total force, that what I had written here, right? So this is the force between this test charge and source charge, which is not here, not in the equation. So that's what that is, okay? And now, so that means this force is basically, this is K Q over R squared. So that's what this force is, and there is this Q. So now what happens is this Q cancels. So field and force equation, they look similar, but they are not same. See, there are two charges in the force equation, but in field equation, because we are dividing force by the test charge, what happens? One charge gets canceled. So only one charge in the equation. So equation becomes a bit simpler. Okay, just K times one charge over R squared. Okay. So this is force per unit charge. That's what we call. So total charge of test charge, I should say. So whatever I said, most of them, I have written that one over here, okay? So source charge produces electric field around it. Other charges experience force in the field, just like a mass experience gravitational force due to another mass, okay? And remember, we had like F, gravitational force, we said is equal to weight, right? And G was F over M. So this is force per unit mass. And this is gravitational field strength. Although we treated most of the time this as acceleration due to gravity, which is true, but its another name is also gravitational field strength, and we defined that way when we talked about gravitational force in physics 1. Okay, so that's what we did, and that's what I'm saying here. Electric field is this. So this is the magnitude you use to calculate field. Okay, this is the magnitude, formula we use to calculate magnitude. How about direction? So let's suppose I have some sort of source charge here, and at this point, what is direction? So let's say this is positive charge. What is direction of E, electric field? See, direction of electric field gonna be same as direction of force on positive charge, okay? And that's why we assume test charge is always positive charge. That's why we assume that, okay? So if this is positive charge, then what's gonna happen? If I were to bring a test charge here, which is always positive by convention, it's gonna experience force that way. So direction of force is that way means the direction of field over there is also that way at that point. However, if this was a negative charge, source charge was negative, then it would be attracting the positive charge. So that's why direction of electric field gonna be that way. Okay. So positive Q and field here, again, the direction has to be always along the line joining them. Okay, so this is positive means direction of field gonna be that way, away from that, radially away, that's what we call it. Okay. Okay, folks, so that is the force and field. We'll talk more about field and field lines in different situations in next class. Okay, so another thing I noticed is many of you haven't done the survey I put in. The link is on Canvas homepage. Hopefully during this weekend, you're going to make time to do it, okay? And I'm gonna show you how to make your own personal tutor using Notebook LM. I have already posted sources or the files in Canvas. So I'm gonna show you, I'm gonna send you a video of doing that. But before we do that, I want you to actually take the survey, okay? So what do you think at this point? And after you use it, what do you think? I like to collect that thinking, okay? So please consider doing it, okay, as soon as you can. Thank you very much. I'll see you next week for the next class.
I have a question.
Sure.